I'm Mohammed Hassan from George Mason University, and today in this talk, we are going to show you how we can offload mobile applications to the cloud more efficiently. Can you hear me? Okay, great. So here's the outline of the presentation. At first, we will introduce the work, followed by the motivation behind the problem. Then we will show some of our preliminary solution and evaluation, and then we will conclude the presentation. So let's begin. So if you take a look at the last few years, you can see that the total number of mobile devices selling per year is increasing day by day. And it is predicted that in the year of 2015, there will be around 1 billion of smartphones shipped to the user. And the increasing popularity of the smartphone are attracting more and more developers to develop more and more application for the mobile devices. People these days use their smartphone for browsing, for watching videos. In addition to that, they also use their smartphone for gaming, optical character recognition, translation, this kind of resource-intensive applications. But these applications were mainly developed for laptops and desktops, so our concern is that how would be the performance of this application on the mobile devices? Especially when mobile devices are lagging behind the desktop and the laptops. So if we compare iPhone 5s and the MacBook Pro, the smartphone and the laptop from the same company, Apple, we can see that the smartphone is lagging behind the laptop in every aspect. I mean, in terms of RAM, CPU, and storage. In addition to that, mobile devices are powered by limited power supply from the battery. So if we continuously watch videos or use our smartphone as the GPS, you can easily exhaust your battery power within 5 to 6 hours. So our concern is that how we can address this challenge, how we can increase the computation power of the mobile devices to save the energy and enhance the response time. Well, there are many hardware and software-based solutions to optimize the battery power consumption in the mobile devices. For example, hardware-based solution includes DVS and DFS. And there are many application-specific solutions as well. For example, if you have both 3G and Wi-Fi for downloading, when you're downloading a huge amount of data, you can always switch back to the Wi-Fi so that you can download a lot of data at the cost of less energy consumption. And lastly, computation can also be augmented with the cloud. So what is the high-level idea here? So you have the mobile device. It has a limited computation power. But you have, on the server side, you have big computers with more memory, more CPU, more storage, more RAM. So what you can do here is that if you have a computation-intensive application running in a smartphone, you can offload it to the cloud. So this is the very straightforward idea that whenever you have any really computation-intensive work, ship it to the cloud. And the related work associated with this cloud-based augmentation can be further divided in two broad categories. One is VM-based cloning, another is task partitioning. So let's take a deeper look at these two things. So in VM-based cloning, what happens here is that the entire image of the smartphone is saved in the cloud, and whenever the mobile device approaches any computation-intensive portion, the computation is offloaded to its cloud counterpart. So let me explain with an example. So for example, suppose you have a translator application running on your mobile device. So it does many things, but what it primarily does is that it takes a Chinese string and translates it to the corresponding English language. I use that string in Google Translator. I hope it means something good. Anyway, so in cloud-based solution, a VM-based cloning, what happens there is that you have this entire image of your mobile phone saved in the cloud server side. So it has the same applications running, and whenever the state in the mobile device changes, the change is propagated, is updated to its cloud image as well. So the application starts its execution on the mobile device here. So whenever it approaches this translate method, which takes a lot of time to do the translation, so at that point, the execution in the mobile device stops. The execution switches to the server side. The server do the translation job here and gives the result back to the mobile device. Once the mobile device gets the result back from the server side, the execution of the application takes its normal way. So in this way, you can offload the computation to your cloud image. Again, here, the problem is that the images between the mobile device and the server side, they has to be continuously synchronized with each other. And we have found that, for example, in the Cloudlet paper, if you want to offload a single method, the overhead is really high, around 100 megabyte of data. So another type of solution to do the offloading is the task partitioning. So here, they don't have a complete image of the smartphone in the cloud, but what they do is that they partition the task and send the computation-intensive tasks only to the cloud servers, which is covered by these literatures. So here again, we are continuing with the same example. Here, what happens is that actually the same application is modified. So here you can see that whenever we are doing a translation job, we are just sending it to the server. You can consider it as some sort of RPC or remote procedure call. And we were really excited when we found that similar type of approaches is also adopted in the industry, something like Amazon Kindle, they have their experimental browser called Silk. And they are also doing some sort of task partitioning there. So browsing has many tasks associated with it, networking, HTML, CSS processing, JavaScript processing, blah, blah, this kind of thing. So what they do is that they push some of the browsing job towards the cloud. But the shortcomings with this approach is that this is not transparent to the applications. Here, you have to modify the application. You cannot just simply download an app from the Google Play and expect that it will work. You have to modify the source code here. So our first goal is that how can we provide a transparent approach for the application for offloading with minimum overhead. And the second challenge is the decision making. So what does it mean? So whenever you offload, let's take a deep look what happens. So you have the mobile device, you have the cloud. So again, we are offloading the translate method here. So what we have to do here, we have to tell the server that, hey, do the translation job for me. Again, translate this string for me. So we have to send the computation and the data. So it takes some time to send the data over the network. So that what I call transfer time. And once the server gets the result, so what it does is that it does the computation there. It does the translation job here, which also takes some time. So the on-server execution time, that means when the application is offloaded to the server side, equals to the transfer time plus the computation time. So when should we offload a computation towards the cloud? Only when the on-device execution time is greater than the on-server execution time, right? Otherwise, instead of gaining performance, we might lose it. So for the decision making, our primary goal is that how can we find this relationship for an application? It depends on many factors. It depends on the bandwidth and the latency between the mobile device and the server. Also on the server, how much the server is loaded, because it has to do the computation there as well. So our second approach is that how we can consider these factors and make a very good decision making. So based on these facts, we also had some literature review that how the decision making is addressed in previous papers. And we found that in ICDC's 2012 paper, they have come up with a threshold-based policy. So the approach here is pretty straightforward. So whenever the size of the data is greater than 6 MB, then they are offloading it. Again, with the continuing with the example. If you want to translate something and the size of the data, size of that Chinese string is greater than 6 MB, then you should offload it. Otherwise, you should execute it locally. But the problem with the threshold-based policy is that it is very difficult to come up with a single threshold value that fits in every environment. So to empirically verify it, we have conducted a face recognition algorithm. So it's a very simple app that you can take a picture of a person and can check the picture of that newly taken person against some previously taken pictures in your database so that this person has any other previously taken picture there. So it takes a lot of time to do the matching with all the images, and it is both computation and data intensive. So what we have found here is that if the bandwidth between the mobile device and the server is around 1 Mbps, then if the size of the image is greater than 33 or 34 kilobyte, then it's worth to offloading. Otherwise, executing the computation in the mobile device gives the best performance. But if the bandwidth between the mobile device and the server raises to 3 Mbps, then if the size of the image is greater than 15 or 16 kilobyte, then it worth to offload it. So here, for this simple two environment, we cannot come up with a single threshold value. For one, it is 15 or 16 kilobyte. For another, it is 33 or 34 kilobyte. So single threshold value doesn't work in this dynamically changing environment. On the other hand, the Maui paper is a very good paper for computation offloading. They have come up with a better approach. What they did here is that they come up with a linear regression model. So they try to predict and compare the on-device and the on-server execution time based on a linear regression model. And they have considered many factors in addition to the size of the data. They have considered the bandwidth and the latency between the mobile device and the server. But we argue that a linear regression model might be too simplified and it may predict some wrong values and some wrong offloading decision. So to verify it, we have compared it with the SVM, support vector machine. And these two figures shows the original value versus the predicted value for these two classifiers. So the more accurate the classifier is, we can expect that the blue line should follow, with the blue dots should follow the red straight line. But actually we have found that, though the figure is a little bit misleading, but we have actually found that the root mean square error for the linear regression model is 3 or 4 times than the SVM. And so is the offloading decision. So our solution is that, our approach is that we have to come up with a more intelligent classifier. And in addition to the size of the data, the bandwidth, and the latency between the mobile device and the server, we are also considering how heavily the server is loaded. That means how much memory and CPU is available on the server side. So based on these things, we have come up with a framework called POMAC, properly offloading mobile application to the cloud. And at first here, we are providing a good decision maker. That means it knows intelligently when to offload it. In addition to that, we are also trying to provide a transparent mechanism for the applications to be offloaded. So for the decision maker, we have considered many classifiers we are still considering actually. So we are considering threshold-based policy, linear regression, support vector machine, knife-based decision tree, and the MLP. And we have found that to classify a single instant, all the classifier takes more or less same time, from 8 milliseconds to 12 milliseconds. But the accuracy differs a lot. The comparatively simple classifier, the threshold, linear regression, and the knife-based, they have a worse accuracy with respect to the higher dimensional classifier, like the support vector machine, decision tree, and the MLP. So we are considering that this classifier might work better for the offloading decision. And secondly, we have also come up with the offloading mechanism. So our first solution was to modify the applications, like that was done in the MOBISys and ICTS's previous papers. But here the problem is that, again, either you have to modify the source code or the binary, which we don't want to do. So actually, without the modification, the offloading can be done, which was done in the OSDI paper 2012, Comet paper, another very good paper. And what they do here is that they have a image of the mobile phone on the server side, and they have a continuous synchronization with updating all the states. And they do some sort of thread migrations, that whenever a thread is executing, working very hard, you can offload it to the server side. But again, the problem with this approach is that you have to maintain the synchronization between the mobile device and the server continuously, which creates a lot of overhead. And the second thing that we may want to try to achieve is that we want to do the profiling of the application, that we want to find the bottleneck in the application, where is the exact point where all the resources are taken over. But this thing cannot be done in the thread migration, because we found that in this paper, OSDA paper, the offloading decision is pretty straightforward. So if the round trip time between the mobile device and the server is RTT, so whenever a thread is executed more than 2 into RTT, then they're migrating it to the server side. So instead of these approaches, we argue that if we could modify the application VM on top of which the applications are running, for Android, it is a Dalvik VM, and inject some sort of RPC type of thing so that we can intercept the method there and offload the particular methods for an application, then it can be done transparently for the applications. And it has low overhead as well, because we don't have to continuously synchronize the image of the smartphone and on the server side altogether. And method level interception, it also gives us the leverage for profiling as well, because we can profile all the methods and we can find where is the exact bottleneck here. So based on these findings, we have come up with a primary framework. In our implementation, we have the mobile device, we have the server side. So the applications all are running on top of the application VM. In this example, Dalvik VM. So whenever the application is approaching any computation-intensive method, we are intercepting the method call by the aim interceptor here. We tweak the code in the Dalvik VM. And we are also monitoring the bandwidth, the latency between the mobile device and the server, how the server is loaded. That means the server side available memory and CPU, and the size of the method parameters, the input size for the particular method. And based on that, we are making the offloading decision whether we should offload it or not. So if the result is, hey, do that job locally, then we are doing nothing. We are just letting the application follow its normal way of execution. Otherwise, through the server interface, we are contacting the server, we are sending the parameters there. Once the server gets the parameters from the mobile set client, then it instantiates appropriate application by Java reflection or Java dynamic class loading. It does the computation there with the provided method and gives the result back to the mobile device. Once the server interface gets the result, it gives the result back to the application by the app method interceptor. It puts the return value in the exact register, and the application can follow its normal way of execution. So we have evaluated our very primary framework with 5 applications, and 4 of them is downloaded from Google Play and the GitHub, and these applications were hand-coded by us. And these applications are Droidslater, Zing, Mesofanti, Picasso, and Madroid. They're mixed of bunches here, and one is translation application, and there's barcode reader, and there is OCR, and there's face recognition app, and another is the calculator app. So here, all the methods, these are the methods names that we are offloading it, and we have found it right now. We are not doing any profiling here, which is our future work that we are doing the profiling as well automatically for a graph tree or whatever. So. And we have evaluated our primary prototype in Android Nexus 1 with 1 GHz CPU and 512 megabyte of RAM. And we have modified the cyanogen mode open source distribution to inject all the code in the Dalvik VM. And we have evaluated our, I would say not evaluate, I would say emulated 5 configurations in our system, in our lab. So we tried to emulate the LAN, wireless LAN, 802.11, 4G, and 3G. Obviously, the latency and the bandwidth varies between the mobile device and the server accordingly. And we are also changing the CPU and the memory in the server side as well. So I really wanted to check that how well the classifiers are behaving with the changing environment. So remember that we have 5 applications. So for each of the applications, we are running 10 instances in each of these settings. So we have total 50 instances for each of the application. And we had different result for different instances of the application. So for some instances, when offloading, it was giving us the best result. For some of the instances, however, if we execute it locally, then we are getting the best result. So this figure gives the average response time and the energy consumption for all those 50 instances for each applications. So the white bar represents the average time when all of the instances, all of the 50 instances are executed on the server side. And the cyan one gives when we are forcing all of them to be offloaded on the server side. Sorry. So the white one gives when all of them are executed on the device, and the cyan one gives the average result when all of them are offloaded to the server side. And we have also manually found out that which one is the best for each of the instances. Obviously, some of them has had better result when offloaded, and some of them had better result when they are executed on device. And the light blue one gives the average of the optimal one. And the dark blue bar, it gives the result for the POMAC here. And here, in our preliminary result, we have found that POMAC is a little bit following the optimal one, and it has really good accuracy, around 70 or 80%. Oh, by the way, we have trained our MLP, multi-layer perceptron classifier, with the 20% of all the instances here at the beginning. So it is some sort of a priori. But we can also expect that because as MLP has a provision of online learning, so maybe MLP can learn over the time and give better result as well in practical field, which we left as the future work. So in conclusion, we can say that mobile devices are constrained by limited power supply, CPU, and memory. And computation can be offloaded with the cloud. So in this paper, our primary goal is to how we can make this offloading mechanism transparent for the applications. And we also tried to come up with a better classifier that instead of blindly just offloading the applications, let's try to be a little bit intelligent when to offload it or not. So thank you for your patience, and I appreciate any question.
Thanks. Could you maybe go over again what the inputs are into your learning models? I wasn't quite clear about that. Like, what kind of signals are you using to learn on? Like, what kind of data are you learning over?
Oh, the bandwidth, these things.
Okay, and how are you collecting these?
Oh, so the bandwidth and the latency actually, there is a whole bunch of another research area that how we can predict it. So we could follow one of them, but those are really, really intensive. So in our next step, actually, we had started to work on. So when the bandwidth and the latency is a dominating factor, when the size of the data that you have to transfer is a huge amount, right?
Right.
So we come up with the magic value, maybe 0.5 megabyte or 500 kilobytes. So if the size of the input parameters is greater than that, then we are just sending 2 packets to the server side and calculating these values. But honestly, those values are not accurate. So maybe we can come up with the moving average or maybe another decision classifier to come up those values.
All right. Cool. Thanks. Okay.
And same thing goes for these things as well, memory and the CPU. Those are not constant. No.
Yeah, that was one of the metrics in the end. The upper graph was latency, the lower graph was energy.
Yes.
Look at incorporating energy explicitly in the model, or are you just train off how much battery life and
Honestly, that's a weak point. That's what I wanted to address in the future work. So what I found when I was doing the work is that the response time and the energy consumption, they are linear. So I was just taking the decision based on the response time, and the energy consumption was behaving similarly. But there are some applications where the result is contradictory. So you have to take a decision by maintaining a balance for both of them. Okay, please.
I think along similar lines, there's also often this accuracy trade-off with the amount of energy that you're going to consume. And from the user's perspective, maybe time till empty, right? So how long is it until I expect my battery to run empty? So another variable that you could kind of throw in there is how much gas is left in the tank, right? And how fast do you expect to be going, and how much accuracy to try and optimize for user happiness, perhaps.
So would you mind if I add another bullet here with that point?